This is brought to you by the Alumni Association of PISJ-ES.
Hey guys, today we'll be talking about air resistance, one of the major forces that we will be encountering in our syllabus. First of all, we will have to understand that air resistance is very much like friction. It's very much like friction. But air resistance takes place in air. So it's like, it wouldn't be wrong if I just call it friction of air. It takes place in the air. Now let's discuss some properties of air resistance. First of all, air resistance is a contact force. And also, just like friction, it's an opposing force. Now let's see, what do I mean by a contact force? And it might not seem like a contact force initially, but it is. Let's see. This object is falling down. It's moving down, and we just threw it from a height, and now it's falling down. And we know, since it acts like friction, it would always be opposing the motion. And since the motion is in this direction, the air resistance would be acting in this direction. This is your air resistance. Now you might ask me, Adil, how is this a contact force? It's just simply air. It's moving. There's nothing in contact. But I would tell you that you are ignoring the fact that there are air molecules. These little guys here. And the situation is something like that these little guys don't want this box to fall or to move. So what they are doing is they're sliding against this box and just applying a force in the upward direction. All of these particles. They're just moving in the upward direction. These little guys here. Sorry. And what our box is doing is that it is fighting these little guys, and it's trying to come down, and it's fighting as much as it can, and it's just continuing its motion. So because there is a contact between the molecules and the box, it is a contact force. And since the air resistance is opposing the motion of the box, it is an opposing force. Also, imagine if there was a vacuum, and a vacuum is the region where there is no air. So if there was no air, there would be no air particles. There would be no air particles. So in that situation, since there is nothing to have a contact with, if I throw this mass in a vacuum vessel, let's say this is a vacuum vessel, there is a vacuum inside, no air inside, and I just throw this box down here. So you would see that there would be no air resistance, since there are no little guys here to force it upwards. There's no one here. There's no molecule here to force it upwards. So in a vacuum there is zero air resistance. So basically these are the properties. Also, air resistance is a viscous force. A viscous force, just like friction, which produces heat. So whenever a box or an object is falling from a reasonable height and there is air present, there will always be a slight warming of this region because of the heat produced during this force. So we have the three properties. It's a contact force, it's an opposing force, and it's a viscous force. And it acts just like friction force. So you will have to make sure you know this. Okay. Now let's see some cases here. For example, the object is moving in this direction, or let's say case number 2 in this direction, or case number 3, this is all in air, everything is in air, the object is moving in this direction, this is the velocity, or the object is moving in this direction, someone threw a box upwards, so it's moving in that direction. Let's see the 3 cases that we will come across when we are doing them. Let's first solve case number 2 because it's easier. Since the motion is in the downward direction, the air resistance would be in the upward direction. In this case, since the motion is in upward direction, the air resistance would be in the downward direction. And since here it's making an angle with the x-axis, the direction of motion, so it will be exactly opposite. The direction of air resistance would be exactly opposite to that of the direction of motion. So these are the few things. Now let's discuss a case here. Let's say, or I think I should first discuss some of the factors affecting air resistance. So there are some factors affecting air resistance. First of all, surface area. Now you have to understand this. Surface area is the let's say the area exposed, or the amount of region exposed to air. So let's say if there is more region let's say exposed to air, so there will be more little guys here pushing upwards. Let's say there will be more little guys pushing upwards compared to an object with a lesser surface area. Let's keep the mass constant. Mass is constant, both have the same mass. For the same mass, if the surface area of this is greater, there will be more little guys here who will be pushing upwards. And here, there will be lesser guys here pushing upwards. So in this case, the air resistance, the greater the surface area, greater the air resistance acting. You have seen a parachute. When a person is falling, he's just going down. But when he opens his parachute, there is an air. We will be discussing about that. But then there is an air resistance acting on it. So second factor would be the second factor would be, let's say, the velocity. Now, the greater the velocity with which the object is traveling, the greater the air resistance. So you would have seen, if you were traveling at a velocity of, let's say, in a car at 20 meters per second, and you open your windows, so what you see is there's just light breeze coming in the car and all. But what if you are traveling at a velocity of 200 meters per second and you suddenly open your windows? What happens is there is a huge gush of air coming in, and you know it's like a very high pressured air coming inside your car. That is because of the greater velocity. The greater the velocity, the greater the air resistance trying to oppose it. Alright? And this also happens with the mass. The greater the mass, greater the air resistance. So these are some factors affecting air resistance, and surface area is a very important one, and we will see how. But before that, we will be discussing a case. Let's see if this is a coin falling initially from let's say 100 meters building. What happens? What are the two forces? What is the first force that is acting on this coin? It's weight of the coin, and it's continuously. That is why it's going down. However, since it's moving in air, there is also a little bit of air resistance. But what happens is, because the air resistance is very less compared to the weight, what happens is the resultant force, let's say the weight is 700 newtons, and this is let's say I'm just assuming 700, and the air resistance is 50 newtons. Force of air resistance is 50 newtons. So the resultant force would still be in the downward direction, 650 newtons. This is your resultant force. That is why it keeps moving downwards. However, let's take the case of a feather. Let's say this is a feather. What happens? Why does it float in air? That is because its weight is very less. Let's say its weight is around 50 newtons. And when you drop it in air, what happens is that there is an air resistance acting on it in the upwards direction. Now, if you notice, the air resistance and the weight are in opposite directions. So what happens is, let's say if this is at, let's say, 40 newtons, it would still be, the resultant force would still be in this direction, because this one is greater. It will still be 50 minus 40, 10 newtons in the downward direction. But if you calculate this, let's say if you calculate the acceleration of this would be very much less than the acceleration of this, because it has a greater resultant force acting downwards. Here there's a very much lesser resultant force acting on this feather. Let's just assume the mass of both of these is 100 grams, the coin and the feather, 100 grams. Let's just find out the acceleration numerically. Let's just see what is happening. Why is this floating and why is this not floating? Let's see. Acceleration is given by force divided by m. This is taken from the same formula, F is equals to ma. So resultant force in this one is 10 newtons divided by the mass. 100 grams would be equals to 0.1 kilogram. So divided by 0.1. The acceleration would be, let's say, 100 meters per second square, which is quite a lot, because I have made these values, so doesn't matter, but we have to compare actually. Now in this case, in the case of the coin, the resultant force is 650 newtons and the mass is 0.1 kilograms. So this becomes 6500 meters per second square. Now you can see it is accelerating at a far greater rate than the acceleration of the feather. That is why this sinks, as in this does not stop. However, a feather is floating here and there and it's not really accelerating a lot. That is the reason